Okay, dilutions of a solution, something that if you're in a lab, you'll do a lot of. When water is added to a concentrated solution, there is no change in the number of particles. The solute particles spread out as the volume of the solution increases, and that is a dilution. So here we are looking at some kind of red dye solution, and as you add water, it gets lighter. Why is this not? Okay. And in general, when you do a dilution, this sort of pretty famous equation gets used. C1V1 equals C2 times V2, where C1 and V1 are the initial concentration and volume, and C2 and V2 are the final concentration and volume of solution. This is behaving strangely. Okay, better. So C1 and C2 can be any kind of concentration, molarity, or the percents, but they must be the same. V1 and V2 must also match. So they can be milliliters, they can be liters, there could be some non-standard concentration. We will always use milliliters or liters. Commonly, you will see the rearrangement of this equation into this form where you're calculating a final concentration and using a starting concentration and a starting volume of the concentrated solution and then diluting it to some volume. And this highlighted portion, that is called a dilution factor. So for example, for a dilution factor, and I think this is an easier way of looking at what's going on. Say you took 100 milliliters of your concentrated solution. C1 is our concentrated solution, and you diluted it to a liter. This is our dilution factor, and when it divides out, you see that it is a 1:10 dilution. So C2 is going to be 1/10 of C1. Okay, just have there. Okay, so here's an example problem. What is the final concentration of when you take 0.5 liters of 6 molar hydrochloric acid and it's diluted to 1 liter? And again, this is one of those cases where let me add where you can look at the dilution factor. I'll solve it with the regular old C1V1 C2 V2, and then I'll show you what I was talking about. Okay, so we have 0.50 liters of 6.0 molar HCl. So this is V1, that is C1. And we're told that it's diluted to a final volume of 1.0 liters. So notice this ratio of the initial volume to the final volume is 0.5 to 1. So this is a 1:2 dilution factor. So right away, we should expect our concentration in the end to be half. But let's do this. C1V1 equals C2 V2. C1 is 6.0 molar. V1 is 0.5 liters. C2 is what we're solving for, and V2 is 1 liter. So when we solve for this, it will be 6.0 molar times 0.50 liters divided by 1.0 liters. And that will be 3.0 molar, which is indeed half of what we started with. It's a handy equation, it's easy to remember, useful in lab. Okay, what else have we got going on here? What is the percent M over V of a solution prepared by diluting 10 milliliters of 9% sodium hydroxide to 60 milliliters? C1V1 equals C2V2. volume 1, C1, volume 2. So C2 is going to be equal to C1 times V1 over V2, 9.00% times 10.0 milliliters divided by 60.0 milliliters, 1 to 6. And let's see, what is that? Equals 9 divided by 6. 1.5. So C2 is 1.50%. M over V. So there's more examples that you can work. Okay, properties of solution. Ethylene glycol is added to a radiator to form an aqueous solution that has a lower freezing point and a higher boiling point. So these are colligative properties, they're called. So okay, they're talking about some things. Okay, solutions versus colloids. Solutions are transparent. They don't separate. They contain small particles, ions, or molecules that cannot be filtered or pass through a semi-permeable membrane. Colloids, on the other hand, colloids have medium-sized particles, cannot be filtered, but can be separated by semi-permeable membranes. Examples of colloids are fog, clouds, and hairsprays, where you have liquid dispersed into a gaseous medium. Dust or smoke, where solids are dispersed in the air. Shaving cream, whipped cream, where gases are dispersed in liquid. Styrofoam, where gases in a solid. Cheese or butter, liquids in a solid. Blood plasma, paints, and gelatin have solids dispersed in liquids. Suspensions are heterogeneous, non-uniform mixtures and have very large particles that settle out of solution. So if you let it sit for a while, you'll see things accumulate on the bottom. Because they separate, they can be filtered. And in order to stay suspended, they need to be stirred. So muddy water, saturated solutions of salt water, those would be examples. Properties of different types of mixtures. So suspensions settle out. Suspensions are separated by a filter. A mixture that has solute particles that do not settle out but are too large to pass through a semi-permeable membrane would be what? Take a pause and think about it. And it is going to be a colloid. Okay, this is the part that I'm more interested in a little bit. Freezing point, lowering, and boiling point elevation. So we know that water has a boiling point of 100 degrees C and a freezing point of 0 degrees C. But if you add components to water, it will actually alter the boiling point and the freezing point. You guys don't have this experience, but in places where the sidewalks get ice on them from freezing, people often throw salt on them because salt lowers the freezing point and it prevents the ice formation. And if you are cooking pasta in boiling water, one of the side effects of adding salt, in addition to adding flavor, is that it will elevate the boiling temperature. And so the water gets hotter than 100 degrees C and the pasta cooks faster. So when a solute is added to water, the physical properties change. The vapor pressure above the solution decreases. And that means that the boiling point of the solution increases. The boiling point is when the vapor pressure equals the atmospheric pressure. So if the vapor pressure decreases, then it's going to take more heat to boil. And the freezing point of the solution decreases. These types of properties are called colligative properties, and they depend only on the concentration of solute particles. And so increasing the concentration of solute particles in the solution decreases the number of solute particles in the surface of the solution and prevents some of those particles from leaving. So in pure solvent, there's just water on the surface, and those are the particles that are going to enter the vapor phase. But if there are solutes in there, they're taking up some of the space of the water molecules, and so fewer water molecules have opportunity to enter the vapor phase. So it's really just about the number of particles. And for ionic compounds, it's the number of particles that break apart when you dissolve something. So for example, if you were going to compare when sodium chloride dissolves into solution, it breaks apart into sodium cations and chloride anions, and you get 2 particles per salt molecule. But if you were to take an equivalent molar concentration of magnesium chloride, instead of getting 2 ionic particles, you get 3. You get magnesium 2 plus 2 chloride minus. And because there are more particles, more ions, this will have a greater impact on the boiling temperature and the freezing point. Okay, so increasing the concentration of non-volatile solute particles in the solution raises the boiling point. More solute particles in solution lower the vapor pressure, and the solution boils at a higher temperature. It requires more heat for them to escape the liquid phase. Adding salt to an icy road when temperature drops below freezing allows the salt particles to mix with the water and lowers the freezing point. One thought is that it breaks apart the crystal lattice structure of ice and makes it harder to form. Adding ethylene glycol to water increases the number of hydrogen bonds that form in solution, lowering the freezing point and raising the boiling temperature. This is what goes into radiators to prevent cars from overheating when they go up mountains in high temperatures. So it's really all about strong electrolytes and the number of particles. So as I said before, 1 mole of sodium chloride gives you 2 particles. I gotta catch up on the slides. Hold on. Okay, because I don't have all the pieces here. So if we're looking at pure water and we're comparing it to I'm not sure what that, it looks like acetic acid, but I would not call acetic acid a strong electrolyte. And we're comparing to calcium chloride. This is the number of solute particles in 1 kilogram of water when you dissolve 1 mole. So if there are nothing dissolved in the water, you get 0 molecules of solute. I'm not exactly sure what this is. C2, but this is a molecular, a covalent maybe this is the polyethylene glycol. Or ethylene glycol, that's probably what this is. So it's a covalent molecule that does not break into ions, and so it just gives you 1 particle when it is dissolved in water. Sodium chloride is a strong electrolyte. It breaks into Na plus and Cl minus, and so you get 2 particles. And calcium chloride gives you 3. And on your overheads that you would have, it gives the freezing point and the boiling point. So the ethylene glycol gives us a slight drop. These are all in degrees C. of the freezing point, and it raises the boiling point by half a degree. Sodium chloride, which has more particles, will drop the freezing point by more and raise the boiling point by more. And then calcium chloride does it even more. So you see, the more particles in solution, the more the freezing point and the boiling point are altered. I'm not going to do a quantitative look at this, and I'm not going to cover osmosis. There's one question on the homework, and I just left it in there because I thought it was interesting about hypotonic solutions, but I won't put it on the exam. So I'm going to stop there. Hang in there, guys. I know it was a long chapter.